Before the Greek astronomer Hipparchus developed his star catalog, the foundation for the Greek model of the universe had been set. The philosopher Plato had helped establish the belief that the earth was flawed, while the heavens were perfect and precise in construction. According to Plato, the planets and stars moved in uniform circular motion, perfect circles on crystalline spheres around the earth. This idea of the geocentric universe, with everything in the heavens revolving around the earth, was a theory that seemed to fit the observations of the time. Visually, it made sense, and although other Greek philosophers had opposing opinions, the apparent motions of the sun, moon, and stars appeared to fit Plato's concept of the heavens.
Plato said that the world, meaning the earth and the sky, was made up of circles, and that all motion was circular, and that the earth lay at the center. And Plato's student, Aristotle, built a model of the universe that worked exactly that way, the earth at the center surrounded by rotating spheres.
Aristotle's model of the universe was constructed strictly from assumptions and observations of the apparent movement of the sun, moon, planets, and stars. In 1514, Nicholas Copernicus drafted a hypothesis, which is an assertion or explanation that can be tested and investigated. Once supported by observations, this hypothesis would lead to new theories of how the universe worked, launching a golden age for astronomy. His hypothesis stated that the Earth rotated on its axis and orbited the Sun, while the Moon orbited Earth. He also hypothesized that other planets also orbited the Sun. This heliocentric model of the universe challenged Ptolemy's geocentric model.
Copernicus lived at a time when everybody believed that the Earth was the center of the universe and that everything went around the Earth. And Copernicus had this amazing idea that the Sun was the center of the universe and everything went around the Sun. Amazing. As he created that idea and created a model based on it, he was really creating a paradigm shift. And the shift occurred then as other astronomers adopted his idea, and they abandoned that view of the universe with the Earth at the center. It's an amazingly hard process of giving up a paradigm, because it influences what you think is a good question, and it influences what you think is a good answer. Ptolemy. He was interested in the mathematics, not so much the philosophy, the mathematics. And so Ptolemy contrived elaborate circles within circles, epicycles revolving as they slide around deferents, epicycles on top of epicycles on top of epicycles.
The reason Ptolemy created this elaborate system was to explain the occasional retrograde motion that the planets exhibit against the background stars. In their nightly march across the sky, the planets occasionally appear to stop and move backward for a time before resuming their eastward journey. Ptolemy's epicycles helped explain this retrograde motion while maintaining the model of a geocentric universe and uniform circular motion. Ptolemy's work was important because it was the first attempt to explain the universe using mathematics. His model accounted for the behavior of the different planets, and some planets displayed retrograde motion and others did not. His model could also predict their future positions in the sky with some degree of accuracy. Because Ptolemy validated Plato's philosophical model of the universe with math, he reinforced a geocentric paradigm, a way of looking at the universe that would last for nearly 2,000 years. Kepler realized that each planet revolves around the Sun, not in a perfect circle, but in an ellipse. This discovery was a breakthrough that corrected the error introduced by the idea of uniform circular motion. In time, Kepler discovered 3 laws that govern the solar system. Kepler's first law states that the orbits of the planets around the Sun are ellipses, with the Sun slightly off-center at one focus. Kepler's second law states that the speed of a planet in orbit varies according to its position, covering equal areas in equal intervals of time. His third law states that the orbital period squared is proportional to the semi-major axis cubed. The farther from the Sun a planet is, the longer it takes to orbit the Sun. But there was even more observational evidence to come that would support a Sun-centered model of the universe.
We scientists sometimes a little too arrogantly believe that we are learning about the truth of nature, the truth of the universe, the reality of atoms and stars and everything in between. Actually, what we are doing the whole time is building belief structures, models. But in the end, all of these ideas of gravity, forces of nature, and the causal relationship between forces and the consequences of those forces are just human ideas. They might have math behind them, but they're still just ideas. They're models. All of what we scientists learn is an ever-increasingly more sophisticated model, a better tested model, a more precise model that allows us to predict the behavior of the entire world around us.
Newton's first law states that a body continues at rest or in a uniform motion in a straight line unless acted upon by some external force. This is known as inertia. His second law states that a body's change of motion is proportional to the force acting on it and is in the direction of the force. The third law states when one body exerts a force on a second body, the second body exerts an equal and opposite force back on the first body.